Alright, so in this video, I'm gonna be explaining an important article with the title Moment Matching for Multi-Source Domain Adaptation. So this paper in 2019. Conventional unsupervised domain adaptation assumes that training data are sampled from a single domain. This neglects the more practical scenario where training data are collected from multiple sources, requiring multi-source domain adaptation. We make three major contributions towards addressing this problem. First, we collect and annotate by far the largest unsupervised domain adaptation dataset called DomainNet, which contains 6 domains and about 0.6 million images distributed among 345 categories, addressing the gap in data availability for multi-source unsupervised domain adaptation research. Second, we propose a new deep learning approach, moment matching, which aims to transfer knowledge learned from multiple labeled source domains to an unlabeled target domain by dynamically aligning moments of their feature distributions. Third, we provide new theoretical insights specifically for moment matching approaches in both single and multiple source domain adaptation. Extensive experiments are conducted to demonstrate the power of our new dataset in benchmarking state-of-the-art multi-source domain adaptation methods, as well as advantage of our proposed model. So you see that we address multi-source domain adaptation where source images come from multiple domains. It could be from domain of sketch, it could be from real, it could be from quick draw, but in each domain we have all classes. So you see the statistics of DomainNet. And here the framework of moment matching for multi-source domain adaptation. Here is moment matching component. Because we have the source, multiple sources, for example, i's domain, j's domain, and then we can do this moment matching component. Because for different classes, it should align not only for the domain, but also for individual classes. So we assume that X1 through XT are collection of IID samples from this number of domains. Then the moment distance between, for example, source and the target is like this. Because the difference between the expectation of source and the target could measure the distance between the source domain and the target domain. So we propose this moment matching model. Our model comprises a feature extractor G. So we have a feature extractor. This feature extractor component that you see. And it consists of all of these things. So here the feature extractor gives us the features. The feature extractor maps D sub S and D sub T to a common latent feature space. So we have the features. The moment matching component minimizes the moment-related distance like this. And then the overall objective is this moment distance between D of S, and we are minimizing over our generator, our feature extractor, and also individual domains. We need to use a cross entropy for classification of individual domains. And in order to align P of Y condition on X and P of X, probability, for example, of a particular sample and probability of the label given that particular sample at the same time, we follow the training paradigm that we leverage 2 classifiers per domain to form n pairs of classifiers. The training procedure includes 3 steps. We train G and C prime to classify the multi-source samples correctly. The objective is similar to equation 2 here. We train the classifier pairs for fixed G. The goal is to make the discrepancy of each pair of classifiers as large as possible on the target domain. For example, the outputs of C1 and C'1 possess a large discrepancy. The output of C1 and C'1. And we define the discrepancy of the 2 classifiers as the L1 distance between the outputs of the 2 classifiers. So these 2 denote the outputs of our 2 classifiers on the target domain, of course, because DT, it means for the target domain. We want to see what happens if we just apply it to the target domain, if there is any discrepancy between them. And finally, we fix C prime. Now that we have found our nice classifier, we fix it and then train G. Now we go back and change generator again, the feature extractor again, to minimize the discrepancy of each classifier pair on the target domain. Now we are minimizing G. And then in the testing phase, the testing data from target domain are forwarded through the feature generator and N classifiers. And we propose 2 schemas to combine the outputs of the classifiers. Average the outputs of the classifiers and derive a weight vector. And the final prediction is the weighted average of the outputs. To this end, how to derive the weight vector becomes a critical problem. The main philosophy of the weight vector is to make it represent the intrinsic closeness between the target domain and the source domains. In our setting, the weighted vector is derived by the source-only accuracy between ith domain and the nth domain. So we introduce a rigorous model for multi-source domain adaptations for binary classification. A hypothesis function H, so the probability that H disagrees with domain labeling function under domain distribution mu is like this. Because f of x is our true domain labeling. And we have a hypothesis to see if our domain labeling is correct or not. So we define this. And for a source domain, d sub s, and a target domain, d sub t, we refer to the source error and target error of hypothesis. So when this expectation is computed with respect to an empirical distribution, we denote the corresponding empirical errors. And so we examine algorithms that minimize convex combinations of source errors given a weight vector. And we define the alpha-weighted source error of our hypothesis H. And now we have an upper bound. If you're familiar with risk and empirical risk, you see that H is a hypothesis space, for example, of VC dimension D, and then let M be the size of labeled samples, and S sub J be the labeled sample size of BJM. If H hat is the empirical, so if this one is an empirical minimizer for a fixed weight vector alpha, and H sub T is a target error minimizer, then there exists n integers. There exists these n integers and n constants such that with probability at least 1 minus delta, it means, for example, with high probability, we can say that we have found an upper bound on that error for the target, of course. And so it depends on many things, like the distance between the domains. And so a toy example could be just two domains, that we see that the triangle inequality implies that this relation holds. So it is not possible to perfectly align the target domain with every source domain if the source domains are not aligned themselves. And because we are doing domain adaptation, we are going from one source to one target. But it is multi-source, so we have multiple source domains and just one target domain. And you see different models and different accuracies.